last class we saw the condition for amplification by stimulated emission, and today we will take it further and discuss about semiconductor amplifier. I have written laser in brackets. Normally semiconductor amplifier here refers to semiconductor laser amplifier, but amplifier itself, the device, we will discuss in detail a little later. So, recall if we pass a beam of radiation of intensity I0 at the input of a semiconductor, then if I0 is the intensity at z equal to 0, then at z equal to L we have I is equal to I0 into e to the power gamma L, where gamma is the gain coefficient. Is the gain coefficient. Gamma is greater than 0 or gain if probability for emission is greater than probability of for absorption. Probability of absorption. The gain coefficient gamma is given by C by n whole square 8 pi mu square 1 over tau r rho of nu into f e of nu minus f a of nu. Rho nu here is the optical joint density of states. We can substitute this here. So, gamma is greater than 0 if this is positive. If this is negative, then gamma is less than 0 and we will have absorption coefficient, and we will see the absorption spectrum a little later today. So, this is the expression for gain coefficient. Today we want to know, and we also have seen that this is positive if EFC minus EFV is greater than H. For all frequencies for which EFC minus EFV is greater than H nu, we have gain or amplification. And from a simple band diagram here, so if EC is here, EV, then if EFC and EFV happens to be in the bands, EFC and EFV, then for all frequencies which correspond to the range between this and this here, that is for frequency for which Eg by H less than nu less than EFC minus EFV by H, we have amplification. There is amplification for all frequencies in this band. So, this determines the amplification bandwidth. So, if I call this frequency as nu 1 and this frequency as nu 2, then we know that the amplification bandwidth, so bandwidth is equal to delta nu is equal to nu 2 minus nu 1. Typically, if this gap is say about 1.4 or 1.35, if you take a indium gallium arsenide phosphide amplifier or any amplifier, if this Eg is let us say 1 eV, and if I say that this separation here is just to get an idea 0.1 eV and this is also 0.1 eV, then what would be the bandwidth? Bandwidth will correspond to delta E, an additional delta E of 0.2 eV. So, delta E is equal to H into delta nu is equal to 0.2 eV. The energy difference here corresponds to a frequency range, and that is here H into delta nu is equal to 0.2 eV. So, delta nu here is equal to 0.2 eV. So, I have to convert it into joules. because H is in joules. So, 10 to the power of minus 19 divided by 6.6 into 10 to the power of minus 34. So, you see how much this will be. So, this is approximately 4 times approximately, and this is 0.2. So, 0.05. So, 0.05 into this is 10 power 15. So, the bandwidth here is approximately 5 into 10 to the power of 13 hertz. Indeed, semiconductor amplifiers have a bandwidth which is of the order of 10 to the power of 13 hertz. What we have got is an expression for gain coefficient and an expression for bandwidth. What we would also like to know is the gain profile. How is the frequency response? If you take any amplifier, normal electronic amplifiers, you would like to know the frequency response. You generally plot f versus gain, and maybe the amplifier has a gain curve like this, and you have the two cutoff frequencies here, f1 and f2, and delta f is this. The gain profile is also very important. There are applications where you need very flat gain profiles. So, we would like to see what is the gain profile of this amplifier. So, we have got this number cutoff frequency, but we want to see the gain profile. So, let us see the gain profile. So, how to get the gain profile? We have to know the variation of gain with frequency, variation of gain with frequency. To begin with, we carry out a thought experiment. A thought experiment is this, an experiment at 0 k. Why we are using 0 k, you can guess, because there are Fermi functions here, Fe of nu and Fa of nu. Fe of nu and Fa of nu, this is equal to f of E2 minus f of E1. We already substituted, you can substitute for the functions here, and you get f of E2 minus f of E1. So, we want to perform this experiment here at 0 k. Now, at 0 k, consider case 1, a semiconductor in thermal equilibrium. We know that there will be no gain, but let us see what we get. So, thermal equilibrium. We have already seen that quasi-Fermi levels, the separation between quasi-Fermi levels have to be greater, and we cannot achieve that at thermal equilibrium. But let us see what would be the profile. So, what we now have is we have a semiconductor. So, this is, let us say, a piece of semiconductor, and incident radiation is passing through this. Let me rewrite this expression, gamma is equal to, because I want to substitute for rho of nu, this is the optical joint density of states. We have derived this expression 1 over pi h cross square twice m r to the power 3 by 2 into h nu minus E g to the power half. Recall the density of states, and we had a plot, if you remember, h nu, and from E g was going like this, because h nu minus E g to the power half is the variation. So, this is E g and this is rho of. So, substitute this expression here. So, I have c by n square 8 pi nu square, there is one pi coming from here. So, 8 pi square and h cross square. So, c by n divided by 8 pi h cross square, 8 pi h cross square. nu square is there. I want to keep nu square outside because I am interested in finding the frequency dependence of gamma. So, nu I do not want to get into this. So, this phi h cross, oh no, let me write as it is, let me not combine. So, C by n whole square 8 pi square, 1 pi I have taken there, into tau r radiative recombination lifetime, into 2 m r to the power 3 by 2 twice m r to the power 3 by 2 into this term is there. So, into h nu minus E g to the power half, and there is a frequency dependence here nu square, this term nu square, because this is independent of frequency, this part. So, h nu minus E g to the power half by nu square into this term, that is f e of nu minus f a of nu, we denote it as f g of nu, where this is called the Fermi inversion factor. Fermi inversion factor. Why, we will see why it is called inversion factor in a minute. So, this difference I am denoting as f g of nu. This is a constant gamma of nu here. So, or gamma of nu is equal to some constant k into h nu minus E g, h nu, this is nu, h nu minus E g to the power half by nu square into f g of. Let us look at the EK diagram of the semiconductor. So, thermal equilibrium, a thought experiment at 0 K, absolute 0. If we see the EK diagram here, let us say the Fermi level is somewhere here. I do not know, somewhere there, this is K, this is EK. EF is somewhere here. At 0 K, the Fermi distribution is given by a step function. So, what I have now plotted here is 0, this is 1, and this is f of t, which means the conduction band is completely full. All levels below the Fermi level are completely full, and the valence band is completely full. So, this is valence band, this is conduction band, and conduction band is completely empty. So, if you take any pair of states, that is a value of energy E2 here and a value of energy E1 here, f of E2 is equal to 0 and f of E1 is equal to 1. Fermi function here behaves like a step function at 0 K. So, f of E2 minus f of E1, so f g of nu, this implies f g of nu equal to minus 1. So, this factor is minus 1. At 0 K, a semiconductor in thermal equilibrium, the Fermi function is somewhere here. You can take wherever you want the Fermi function. You can take a degenerate semiconductor also and see that you will get f g of nu equal to minus 1. And therefore, the gain coefficient here gamma is equal to minus k into this. So, how would this look like? So, let us plot. Nu, what is nu? Nu is the frequency of radiation. We have seen that the typical bandwidth is delta nu is of the order of 10 to the power of 13 hertz, 10 to the power of 13 hertz, and nu is of the order of 10 to the power of 14 hertz. the frequency, 2 into 10 power 14, 3 into 10 to the power 14, 4 into 10 to the power 14, that is the kind of number that we have. Therefore, our interest is to find the amplification response. So, the bandwidth here is approximately, in our case, delta nu is of the order of 10 to the power of 13 hertz. So, in the range of interest here, the frequency, the absolute frequency itself varies very little. That means, for example, you see this is 10 to the power of 14 hertz, means this end is 10 to the power of 14 plus 10 to the power of 13. A small number. If this is 1, this is 1.1. So, the variation of nu square over the interval, that is actually if I plot nu square, that will have a variation, it is actually 1 by x square, please see it is 1 by x square. However, the range of interest where x varies very little, and therefore, I can either assume it as almost a constant. Over the range of interest, this is 1 over nu square variation is almost constant, because 1 by x square. So, starting from 0, if you take 1 by x square, it drops like this, as you know, 1 by x square. However, we are considering a small range. This is if you take from 0, our frequencies are just 10 to the power of 14 plus minus 10 to the power of 13, which means we are looking at a small variation here. Therefore, 1 by nu square varies very little, and therefore, the variation is primarily determined by this. So, at 0 k, we have gamma of nu is equal to a constant k 0 into f g of nu is minus 1. So, minus k 0 into h nu minus E g to the power half. Please see that 1 over nu square dependence is very small, because our range of interest is very small. If you wish, you can keep and plot, then also it does not make much difference. This starts from E g, this is h nu, I am plotting the gain coefficient gamma. F g, let me plot, because it is negative, I need to plot negative as well. So, it starts from here E g, and this would h nu minus E g to the power half would vary like this. Therefore, minus h nu minus E g to the power half would vary like this. This is gamma is 0, gamma positive, gamma negative. We already know this, that at thermal equilibrium gamma is negative, because f g of nu is minus 1. I want to keep this graph here, and let us see now, let us go over to quasi-equilibrium. So, case 2, quasi-equilibrium. So, case 2, quasi-equilibrium. The same EK diagram, let me draw in parallel, but now we have pumped this semiconductor and assume that EFC is already in the band, EFC and EF. Because we know that we get gain only if the difference is greater than h nu. Therefore, EFC is here and EFP is here. What does this mean? EFC, therefore, the variation here would be and the variation here would be so on this axis I have plotted f of E. this is 1, 1.0, this n is 0. Corresponding to two Fermi functions which describe the occupation probability of the two bands. At 0k, the valence band is completely full up to EFV and the conduction band is full up to EFC. Therefore, if you now consider a level E2 here and a level E1 here, note that f of E2 is equal to 1 and f of E1 equal to 0, implies Fg of nu equal to plus 1. So, you see the Fermi factor has been inverted. Earlier it was -1 at equilibrium, thermal equilibrium, and in quasi-equilibrium Fg of nu is plus 1. So, what do we expect the gain profile to be now? This one. So, the gain now in this case, the gain goes up like this. How far will it go? This is h nu, the photon energy. So, let me just for differentiation, let me show this like this. So, this is for case 1. So, this is case 1. How far will it go? H nu is the photon energy increasing from Eg. It is increasing from this gap. This gap is Eg, so it is increasing. When it comes to EFC and EFP or beyond this, this is 0 and this is 1. So, the factor is inverted at EFC minus EFV. So, along this line at EFC minus EFV, at the point EFC minus EFV, the factor suddenly becomes from plus 1 to minus 1. When energy h nu comes here, that is becomes more than this difference. When it comes here, then this is 0, this is 1, and therefore, the factor in reverse, and therefore, the gain profile drops down like this and continues on this line. So, let me redraw this here. So, h nu beyond Eg, it starts increasing as h nu minus Eg to the power half drops down this and continues here. So, this value here is Eg and this value is EFC minus E. What is this? On the axis is gain profile gamma. So, gamma versus h nu. So, this is the frequency band in which amplification takes place and the gain profile looks like this. This is at t equal to 0. What will happen for t greater than 0, normal temperature? First thing you see is the Fermi function gets smeared. So, the Fermi function does this. So, at 0.5 it has to cross at 0.5. So, this is the Fermi function. So, this is for t equal to 0k and this is t greater than 0. This also smears. So, we have this variation. Whatever be the temperature at EFC and at EFV, the probability is half. So, it is 0.5 here and 0.5 here, which means f of EFC minus f of EFV is half minus half, that is 0. So, Fg of nu equal to half minus half equal to 0 for h nu equal to EFC minus EF. Fg equal to 0. Fg equal to 0 means what? Where is the gain expression? So, it was multiplied by Fg of nu here, Fg of nu. Fg of nu equal to 0 implies gain equal to 0. And therefore, first point is at EFC minus EFV gain is 0 even for t greater than 0. The gain is 0 here. Second, if I take a frequency close to this, that is close to Eg, which means close to the band gap here, you see f of E2 is here. I have actually shown like this, but in practice, as you know that this smearing is very little, or f of EFC is close to 1 but less than 1, it is close to 1 but less than 1, and f of EFV here, that is if I take at Eg, so please see this, h nu corresponds to Eg, h nu corresponds to Eg means E2 is here. So, the corresponding f of E1, f of E2 is close to 1 but less than 1. Corresponding to E1 here, f of E1 is close to 0 but greater than 0. So, just if I say that if this is 0.99 and this is 0.01, the difference is 0.098. As you increase, this becomes smaller and this becomes lesser and lesser, it is going towards 0.5 and this is also going towards 0.5. Therefore, the difference drops down from 0.1 to 0.0 to 0.1 to 0, which means here near Eg it is almost the same, but the difference increases and finally here it comes down to 0. Let me draw this and then this is for t equal to 0, this is for t greater than 0. The difference near Eg, the Fermi inversion factor Fg is close to 1 but less than 1, and therefore, the multiplying factor is slightly less than 1. So, you see it starts, but as h nu increases, the multiplying factor becomes smaller and smaller, and therefore, the difference between t equal to 0 and t equal to t greater than 0 changes. And we know that whatever be the temperature, the 0 crossing is this. So, if you actually put the numbers and see that you will get a gain curve which is like this. This is the gain profile. So, if I want to independently plot the gain profile, then so if I plot gain, then you will have the gain taking a shape something like this. So, this is gain. Let us say at room temperature T greater than 0. This value here is, if this is frequency, like you typically plot the frequency response, then this value here is Eg by h, and this value here is EFC minus EFV by h. I have not shown beyond that, because beyond that it is negative. I am just plotting the gain profile, and typical bandwidth is 10 to the power of 13 hertz. These are practical numbers of semiconductor optical amplifiers. In theory, it looks as if the gain starts right at Eg, and at EFC it is as if you see it is starting here and it is like 0. But in practice it is slightly different. The shape is the same, but the ends are slightly different because of band tail states. These are highly doped semiconductors, and therefore, there are band tail states, and this tapers down in practice. like this, and similarly it tapers to this side. It is not an abrupt band, this tapers down here and it looks like it is not flat. The first thing that you see that semiconductor amplifiers, semiconductor optical amplifiers do not have a flat gain profile. And this is one of the reasons why in all WDM communications we do not use semiconductor amplifiers, but we use erbium doped fiber amplifiers which have a flat gain profile. But the bandwidth in this case is quite large. So, we know why this shape of gain profile that we have. So, the summary is that if you pump a semiconductor and maintain the difference between the quasi Fermi levels greater than the frequency h nu at which you need gain, then it is possible to have gain. How do we pump the semiconductor? How to maintain? So, the next question would obviously be how to have EFC minus EFV greater than each. It is not going to be easy. We can have quasi Fermi levels, all PN diodes when you forward bias you have quasi Fermi levels, but you are asking for too much, that is EFC minus EFV greater than EG. So, how to pump? Any amplifier requires a pump. How to pump so that, the question is incomplete there, how to pump so that EFC minus EFV is greater than EG, greater than h nu for the frequency nu, but minimum is EG, therefore, I have written how to make it greater than EG. The easiest way is by current injection. The answer, I am writing the answer first and then we will discuss by current injection in a forward biased PN junction. A forward biased PN junction. So, what do we mean by this? So, you take a PN junction, we have already drawn the band diagram. So, I will directly draw the band diagram. So, what we have is this is the P side, this is the N side, and we have Fermi level here. This is axis energy, this is the distance x. Before pumping, and there is a built-in voltage, built-in potential. So, this is V built-in. E into V built-in is the energy. So, when you forward bias the diode in our basic elementary picture, so we have forward bias. So, this is P, this is N. Originally there was a depletion layer here and U forward bias. I can also plot the carrier profile across the junction. Very quick recall of the basics that we have already studied. So, if you plot the carrier concentration, so this is P and this is N. So, P comma N. So, what I have plotted is whole concentration P and this is and this is the same x across the junction. So, on this side there are very little electrons. This is not Fermi level, this is the concentration n of x. So, what I have plotted is n of x and p of x across the junction. On the p side you have large number of holes, and on the n side you have. What happens when you pump? When you pump forward bias, this goes up. We already discussed that. This goes up, which means the band now comes, let us say here, and this band here. So, this is the new position. Let me draw them with the solid line itself and differentiate by putting crosses, because, so let me draw in this fashion just to differentiate the second case, that is after forward biasing. The Fermi level has to separate out because the Fermi level has to remain. So, the Fermi level, this one is here and the next one has moved. So, EFC and EFV. So, what we have is EFV and EFC. The Fermi levels have separated out. Good. You pump harder, this will go further up. How much will it go? When you pump harder, please see this is full of electrons here. Electrons are coming here. So, when you forward bias, the carrier profile now becomes like this. So, far away from the junction there is very little change, but at the junction now the carrier profile has changed. Please see, this was before biasing. How do I show? Okay, let me put dots just to differentiate. This is after forward biasing, and P profile has also moved like this. So, this is after forward biasing. So, what has happened is at a given value of x, you see that both n of x and p of x have increased. That is what you see here. For if I had taken this value of x here, then earlier the number of electrons here was much less, but now we have large number of electrons. Similarly, holes which were here have also moved to this side now, and that is why this has also moved to that side. This was n of x. Please see, at any value of x, if I take this as the x, then this value here is p of x. After forward biasing, this is, so this is p of x. After forward biasing, this is the new p of x, which means this value now represents p of x plus delta p of x. Similarly, you have n of x and delta n of x. The delta n of x, we are looking at the junction region. Please remember, we are looking at the junction region because the changes occur in the junction region because of forward biasing. Delta n of x and delta p of x, we have got in the junction region delta n of x and delta p of x. Originally it was just n before forward biasing, now it is this. This delta n of x and delta p of x are called excess carrier concentration. So, this is excess carrier concentration, excess carrier concentration. N and P were called carrier concentration. The delta n of x and delta p of x is called excess carrier concentration. And the point that we see is the Fermi level has separated out. If you pump harder, the level goes further up. At best, the two levels, let us say, got equal. Means I have lifted this, the two levels have become equal. This is the p-n junction. original junction. Now the level has been raised. Where is the Fermi function for this? It is here. Where is the Fermi function for this? Far away from the junction. Please see this. This is the Fermi function of the p side. This was the Fermi function of the n side. So it is still less than EC. This is now EFC. This is now EFV. Therefore, and this is EC and this is EV. What do you see? EFC minus EFV is still less than EG. This is, I said this is at best. Why am I saying this is at best? By the time you forward bias it so much, the current through the device is so high that the junction will burn up by this time. There is no barrier. Any electron injected here is simply going through the device. This is very, very high forward biasing and the junction will simply burn up. Yet you have not reached the condition EFC minus EFV greater than EG. So how to achieve this condition EFC minus EFV greater than EG? Can we think of something? Yes, one of the ways is we start with highly doped P and N, so that degenerate P side and degenerate N side. If we start with the degenerate P semiconductor, which means EF is already inside here and EF is already into the conduction band, in that case I can have EF sitting here and EFC sitting there. Please see, if I start with a degenerate semiconductor, there is a possibility of making EFC minus EFV greater than, so EFC, EFV minus EFC greater than EG. So first point is we have to use, it is necessary to use highly doped P and N materials to realize a p-n junction for a source which can act as an amplifier. Even this is not a very practical solution. It is all right, in theory it is possible, but as I said, to achieve this kind of forward bias means the current through the device is so high that it will damage the junction. A more practical and correct way of getting this is by the use of double heterostructures, and which brought in, as I said, Nobel Prize for that discovery. So use of double heterostructures. That is why we discussed double heterostructures in details and trying to draw the band diagram of double heterostructures. Yes, the method is by current injection, but in double heterojunction, double heterostructures, p-n junctions which form double heterojunctions. So we recall the band diagram very quickly, and now you see what happens. That leads to carrier confinement, and the separation between EG and EFC and EFV can be easily greater than EG. So recall the technique that we have for drawing the energy band diagram. So we have a double heterostructure with a low band gap material sandwiched between two high band gap materials. Highly doped P structure. So let me draw the P here or inside the band. Okay, let me, for simplicity, let me draw it here. That's all right. And then we have another structure here which could be slightly P doped or N doped or intrinsic, and I take a highly doped N side here. So this is N plus, this is P, this is P plus. This could be aluminum gallium arsenide gallium arsenide and aluminum gallium arsenide. So, we join the, let us check the band diagram. So, one of the, as I said, you could start anyway. So, let me take the middle one here and show the Fermi energy here, and then we know that before forward biasing the Fermi energy should remain constant, and it is p to p plus, therefore, the band will start bending like this here. So, the band, so let us, the band will bend here, and then there is a discontinuity. The Fermi function is here, therefore, E. So, this is EC, EC of the p side, this is EC of the n side, EV of the p side and EV of the n side. So, very quickly, so the band starts bending like this, then it meets a discontinuity. So, I have a discontinuity and then the band continues. So, the band continues. When it reaches this junction, this is a p-n junction. So, the band has to, so here also we have plus a potential energy variation like this, here also we have a potential energy variation like this. So, the band starts bending further, but it meets an upward discontinuity. So, we take this up, this discontinuity here, and then this continues further, and because finally the Fermi level has to be here. Similarly, this end, that is this end, starts from here, starts bending, but there is an upward discontinuity here. So, this bends upward and then continues on this, comes here, this has an upward discontinuity, a downward discontinuity, sorry. So, here there is a downward discontinuity, this discontinuity, so downward discontinuity, and then we have the band continuing. I have shown a little, actually the angle should be more because it is n plus, so rapid drop. This is the advantage of chalk and board. I can wipe whatever mistake I make. So, this is the structure. Recall that this is, there are plenty of electrons here because this is a degenerate n semiconductor. Plenty of holes here. I just have to draw one diagram of forward biasing and then we will stop. More of discussions we will do later. Is the diagram all right? Clear? So, this is the p side, p plus, this is the n plus side. We have not forward biased yet. So, we are forward biasing now. So, we apply positive voltage to this end and negative to this side. As usual, this will start going up. So, this starts going up. So, let me draw the diagram separately here rather than showing it there. So, very quickly, so this discontinuity, then we have this, then we have this, and then I am now showing the forward biased, right. So, originally I had this here, similarly from here I have this, an upward discontinuity continuing like this, and then from here there is a downward discontinuity, and let me show like this. When I forward bias, this end is raised, and therefore, we have the new diagram which is coming. So, everywhere this portion gets raised here, and this comes here. So, originally it was here, now this has come to this, and therefore, the Fermi level here, Fermi level was inside the band. So, the Fermi level is here. So, EFC. Do not worry, you just have to see. I have raised this, and therefore, EFC is here. EFV was here. So, EFV. So, this also came up now. So, this got raised, this got raised, discontinuous, because the band gap has to remain the same. And this was here. The layer which is here, that is the sandwiched layer, is of thickness approximately 0.1 micrometer. It is smaller than the junction width in normal PN junctions, and you have electrons, because of forward biasing, electrons completely filling here, because this has been raised, and because this level went up, you have holes after forward biasing. What has happened? Look at the junction region here. This was the P plus region and this is the N plus region. This is the junction region. In the junction region, EFC is already here. Why EFC is here? Because the number of electrons are so large that the Fermi function has moved here into the band, and number of holes are so large that here the Fermi function has come into the band. Now, this difference you see, this is the difference which is larger than Eg of the sandwiched layer. The difference between EFC and EFV is larger than Eg of this layer, the layer which was sandwiched, the low band gap material. Second point, first, therefore, you can clearly see that EFC minus EFV can be greater than Eg. Second point, the carriers, the number of carriers here, number of carriers in a small volume is so large that the excess carrier concentration delta N and delta P become very large. We will put some numbers and quantify this. What is this very large? Become extremely large. Because these numbers become very large, you know that you recall EFC and EFV by Joyce-Dickson approximation. You recall this, EFV is equal to EV minus KT into ln P divided by NV plus 1 over square root of 8 into P divided by NV. This is the Joyce-Dickson formula which we have discussed earlier, the empirical formula ln N divided by NC plus square root of 1 over 8 into N divided by NC. The carrier concentration N and P have become very large because of the pumping. Excess, this P is the original P plus delta P. Delta P is due to current injection. So, these P have become very large, P and N, and therefore, EFC and EFV, EFC becomes greater than EC and EFV becomes less than EC, because this is now a larger number, a positive number, and you can clearly see that EFC minus EFV becomes greater than EG. So, EFC minus EFV becomes greater than EC minus EV because both the quantities here are positive large quantities. If this small n is less than NC, then this part will become negative, log of negative fraction. But now when n has become very large, it becomes positive. We will put some numbers, or you will put some numbers and see, but this is why double heterostructure are used in all laser devices. To achieve EFC minus EFV greater than EG in a practical way by passing very small currents, as we put numbers, we will see that just by passing milliamperes, we do not have to pass hundreds of milliamperes through the PN junction or fear of burning the junction. So, we will stop here and continue in the next class.